We're going to take our notes on scientific notation in two separate videos. So when this video is over, you can go to the next video to complete your notes. So scientific notation is a compact way of writing very large or very small numbers. The next little sentence gives us kind of the definition of how we write numbers in scientific notation. So it has this form, a times 10 to the n, where a is a single digit. So 1 is the smallest single digit, can be up to 9. So it's anywhere between 1 and 10, including 1 but not including 10. So then they go through the steps of how to write a number in scientific notation. So we move the decimal, so the new numbers between 1 and up to 10, and then we write using a power of 10. If the decimal point is moved left, the exponent is positive, and if the decimal point is moved right, the exponent is negative. But I don't suggest you kind of memorize this. Instead, think about whether the number is big or small or how you've changed it, because when we're converting from standard form back to scientific, it's going to be exactly opposite. So let's do a few examples together. So for number 1, they have 540, that's written in standard form. To write that in scientific notation, we first need to move the decimal point. So the decimal point is actually after the 0. If there's no decimal point there, then it's understood to be after the number. So the decimal point's there, and we need to move it so that there is only one single digit in front of the decimal point. It can be any digit 1 through 9. So we move it twice to the left, so it would be in between the 5 and the 4. So we'd have 5.4. Now, obviously, 5.4 and 540 are not the same number. If you look at 5.4, it's significantly smaller than 540. In fact, it's 100 times smaller, because every time you move the decimal point once to the left or right, you change the size of the number by a factor of 10. In this case, since we moved it twice, we made it 100 times smaller, 10 times 10. So 5.4 is 100 times smaller than 540. So in order for, we want these two numbers to actually be the same number. We want these to be equivalent. So in order to make this the same size as 540 or equivalent to 540, we would need to multiply it times 100. But we're going to write 100 as 10 to some power, which would be 10 to the second power. And it's not a coincidence that we move the decimal point twice and that the exponent for the 10 is 2. We'll see that that is consistently the case. So for the next one, our decimal point is after all those zeros. We need to move it so that there's just one digit in front of the decimal point. So we move it in between the 9 and the 3. So we're going to have 9.37 or 9 and 37 hundredths. But obviously 9 and 37 hundredths is significantly smaller than 937,000, and so we need these two numbers to actually be equivalent. So we're going to multiply this times the power of 10. When we moved it 5 spaces to the left, right? 1, 2, 3, 4, 5. Yeah, 5 spaces to the left. We made it, what would that be? 100,000 times smaller. So we need to multiply 9.37 times 100,000, or 10 to the 5th, which is what 100,000 is. To figure out, though, that it's a 5, you don't need to know that it was 100,000 times smaller. You can just count how many times you move the decimal point to the left. We moved it 5 times, and so each time we moved it, it decreased the size. It made it 10 times smaller. So we need to kind of undo that 5 times, because we did that, we moved 5 times. So for the next one, there's the decimal point. We move it back in between the 1 and the 8. And then we count out how many times we moved the decimal point to the left, and it was 6 times. So it would be 1.852 times 10 to the 6th. For the next one, the decimal point starts there. We move it to the left so that there's just one digit in front of the decimal point. And then we look and see how many times we move the decimal point, and it was 4 times. So we'll multiply it times 10 to the 4th, because 7.682 is way smaller than 76,820. So we need to multiply 7.682 times 10 to the 4th so that the numbers are the same. And for number 15, is that 15? No, I'm sorry, 5. For number 5, The decimal point is after the 1, so we move it in between the 4 and the 6. And since we move the decimal point 3 times, we multiply times 10 to the third. So now if we look at number 6 is a small number, right? 1 through 5 represented larger numbers. These are smaller numbers. So there's the decimal point. Right now, there's a 0 in front of the decimal point. We need a single digit, 1 through 10, not including 10, to be in front of the decimal point. So we now need to move the decimal not to right in front of the 9, because that would still leave a 0 in front of the decimal point. We have to put it in between the 9 and the 8. So now we're going to multiply by a power of 10, but notice 9.82 is now actually bigger than the original number. So we need to make 9.82 smaller. We made when we moved that decimal point, we made the number smaller by a factor of 1,000. So it was like multiplying it by 1/1000th. I'm sorry, bigger by a factor of 1,000 when we moved it to the right. So we need to undo that. We need it to be smaller, right? Because 9.82, that's a whole number. Obviously, that's way bigger. So we need to balance that with the factor of 10. So we need to use a factor of 10 that will divide out that 1,000, or they'll make it 1,000 times smaller. So it would be 10 to the negative 3. Because 10 to the negative 3, right, we just did this when we were talking about negative exponents. That's the same thing as 1 over 10 to the third, or 1/1000th. Right. So when we move the decimal point to the right 3 times, we multiplied it by 1,000. And now when we multiply by 10 to the negative third, that's like dividing by 1,000. So we're kind of back to the equivalent of what we started with. For the next one, we need the decimal point to move in between the 5 and the 2. When we moved it twice to the right, that made it 100 times bigger. So we multiply by 10 to the negative 2 to then make it 100 times smaller. For the next one, we moved the decimal point in between the 1 and the 4. We moved it 6 times to the right. So to balance that out, we multiply times 10 to the negative 6. When I'm trying to figure out if it's positive or negative, I look at my numbers. I look at the original number, and I notice the original number is really small. And I look at my new number, which is significantly bigger. And I need them to be the same number in the end. So I know I have to multiply by a negative exponent, because 1.4 is too big. It's not equivalent to the original. So I would need to multiply by a negative because it's too big. For number 9, we just need to move the decimal point once in between the 2 and the 5. So that made it 10 times bigger, so we need to make it 10 times smaller using our factor of 10. And then for number 10, we have to move that decimal point a lot. So it's in between the 7 and the 2. We moved it 9 times to the right, so we'll multiply by 10 to the negative 9th to counteract that multiplying by 10. Every time you move it to the right, you multiplied by 10. So you multiplied by 10 to the 9th. So we undo that by multiplying by 10 to the negative 9th. Okay. At the bottom, they're asking us to figure out if these are correctly written in scientific notation. So if we look at number 11, the digit in front of the decimal point, there's just a single digit, so that's okay. And then it's times 10 to some power, so that's fine. So this, yes, this is written in scientific notation. But for number 12, if you look at number 12, it kind of looks from a distance like it is, but notice that in front of the decimal point there are 2 digits, right? And there should only be 1. So they say that if it's not written in scientific notation, then correct it. So we could just leave it and move it over. But what they mean is correct it so that the new number that you write is equivalent to the number that they wrote. So if we move the decimal point once to the left and have 1.14, when we move the decimal point to the left, that makes the number smaller. So we need to balance that out using the factor of 10. So we need to make that 10 times bigger. So we made like this part of the number 10 times smaller. So we're going to make this part of the number 10 times bigger. So we'll multiply by 10 to the 4th power. So that one was no originally. and now we fixed it so that it is. For number 13, same issue here. If you look, the decimal point has 2 digits in front of it, so it should be, the decimal point should be in between the 8 and the 5. So now to write an equivalent number, obviously it would be 8.51. When you move the decimal point to the left, it makes the number smaller. So we need to balance out in the factor of 10 and make the number bigger. So we need to add 1 to the power of 10. Notice that that doesn't take it to -6. It actually takes it to -4 because we need it to get bigger, and -4 is bigger than -5. And for number 14, that is actually written in scientific notation, so we don't have anything to do to that one. All right, and now we can move on to the next video.